Part 1. The fundamentals of structural stability. The content will be stability equilibrium, states of equilibrium, potential energy due to a force, elastic potential energy, principle of total potential energy, examples of total potential energy, example of use of total potential energy to find equilibrium condition, the effects of axial forces on bending, energy criteria for stability, stable symmetric bifurcation and the calculation of elastic critical load, direct calculation of elastic critical load, refined axially loaded column, the buckling of struts, stroke Euler loads. State of equilibrium. Consider a load structure subjected to a small additional load. It is a position of stable equilibrium if, after removal of the small additional load, the structure returns to its original loaded position. If it does not, it is a position of unstable equilibrium. Example of stable equilibrium, unstable equilibrium, where you can see the stable equilibrium. This one, if you push this way and here is the support, the simple support, it can be able to return to a original position because of gravity. But in this position, it cannot be able to return to original position. This one is both stable and unstable. That is stable in the direction y, unstable in the direction x. States of equilibrium. An equilibrium and its state can be determined using the total potential energy of the system. First derivative gives the equilibrium condition. The sign of the second derivative indicates the state of equilibrium. This energy-based approach is an alternative to the state method, that is EBA, and is an alternative to the state method that is based on Newton's equilibrium condition, but is more general and convenient. It can be applied to more complex problems and form the foundation of finite element method. Definition of total potential energy. The total potential energy is equal to the sum of the potential energy due to loads, that is V, and the elastic potential strain or energy U. So total potential energy TPE is equals to U plus V. Potential energy due to force. Potential energy due to force, e.g. external force, gravity force, can be given by this curve here of y against x. So by definition, V should be equals to force multiplied by x. For example, gravity, V should be equals to this matrix multiplied by this matrix, which is equals to mgy. Elastic strain energy of basic members. Linear spring. A truss member is equivalent to a linear spring with equivalent stiffness K. K should be equals to EA over L. That is, K represents the equivalent stiffness. Number 2, torsional spring. Torsional spring, as seen in these images, stores strain energy when subject to a torsion to undergo angular deformation. So it is torsional spring stores strain energy when subject to a torsion to undergo relative angular deformation. If you struggle to understand how torsional spring work, just check and play with cloth pegs to help you know its mechanism. Axial deformation. Axial deformation is treated as a truss member, as you can see in this formula, where equivalent stiffness K should be equals to E A over L, and elastic potential energy U should be equals to a half, that is the area under this area under here, which is of course an angle, should be equals to a half multiplied by the base times height, that is half T times that displacement, which should be equals to a half times the constant, that is EA over L, that is the equivalent stiffness, times the displacement squared. T should be equals to phi over A, should be equals to E over displacement over L times A. U is an integral of a half m over r, which can be simplified into a half m squared over EI, and further simplified into a half EI over r squared, and further simplified into a half EI over d squared over d x squared, as shown in this formula. M is equals to EI over r. Therefore, 1 over r is equals to d squared over v over dx squared. That is in the beam bending case. Principles of total potential energy. Total potential energy of spring with applied constant force should be equals to half Fd, which is equals to half k d squared, that is the displacement. Total potential energy of the system should be equals to now U plus V, that is now half k d squared minus Fd. Total potential energy tip E, that is assume theta is function of d to dn, where I is equals to 1 to n, that is 1, 2, 3, 4, 5 up to n. So the principal of total potential energy of all displacement configuration compatible with support position, the one which satisfy equilibrium, correspond to a position of stationary total potential energy. It is very important to identify the correct number of independent displacement for a given structure, but there may be many options which variable can be used. So total potential energy is given as follows. Equilibrium condition should be equals to 0. So in terms of potential energy is zero derivative. The first derivative defines equilibrium but does not show if the equilibrium is stable. Example of using TPE to find equilibrium forces. Can see a simple supported cantilever here with this force here and this force here. Now it's being supported here by a spring and a spring here. So this is the assumed displacement. Now based on the equilibrium, so RD and RC are the forces in the spring. Now you can find the spring forces with this formula. The effect of axial force on bending moment. Consider a beam subject to a lateral force 2W and a pair of axial P. Column bending under axial P can be shown in this diagram, and a spring bar model can be shown as seen here. Equivalent spring stiffness can be determined as K is approximately EI over L. 0.5 should be less than 5, which should be less than 1. How buckling happen for a spring bar system? A spring bar system has one DOF, that is the simplest system. The bar is rigid and has one DOF. The full behavior of the system when P increases can be analyzed by full geometrically exact assessment through a theta times but for computing the buckling load, the second order approximate method, that is the P delta analysis, is sufficient. So in field data analysis, both the internal and external energy term include quadratic terms. So there is a load-induced stiffness term that can be cancelled to the standard stiffness, causing buckling. The effect of axial, that is the P delta effect, can be shown in this diagram. Observe the lateral stiffness is the function of the axial force P. The larger the P, the smaller the stiffness K. When K is 0, the column has 0 lateral stiffness with respect to the force W. Energy criteria for stability for a single displacement or rotation. The formula can be expressed as Taylor series above the position D as shown. Usually, determination of the sign of this term, second derivative, is sufficient to assess stability. So this is the full geometry exact assessment through this formula. And the second order approximation method is field delta analysis. The P critical, that is elastic critical load, is equals to stiffness over L. Observe that this is a nonlinear equation with respect to theta. That is, phi is equals to half times stiffness times theta squared minus PL 1 minus cos theta. So P has any value. When P has any value, it's a trivial solution. When P does not have has exact value, is non-trivial solution. So equilibrium paths as shown in this diagram. Equation 1 and 2 define equilibrium path 1 and 2. All points on the paths are in equilibrium. P1 is called the primary or fundamental equilibrium path. P2 is the secondary or post-Buckling equilibrium path. The intersection of P1 and P2 is called the bifurcation point. So stable symmetric bifurcation, that is assessment stability equilibrium through the first method, that is full geometric exact assessment. Can be shown in this formula, where if the answer is greater than 0, it is stable. Elastic load buckling is the load at which the primary equilibrium path ceases to be stable. Elastic critical load buckling load is the load at which the primary equilibrium path ceases to be stable. Assessment of the elastic critical load has two approaches. Geometrical exact assessment through delta phi, or short method, that is the P delta analysis method. Observe that, so this direct calculation of elastic critical load. Observe that this is a linear equation with respect to theta. Stability of equilibrium can be assessed similar to the geometric exact approach. Buckling load for 2 DOF spring bar system. So multiple degree of freedom system. Define axial load column model with more than 1 degree of freedom. So you can see in this diagram, so to compute the buckling load, you should follow the below procedures. So you have to identify independent variable. There are many options. Find out the relationship, assuming small definition to simplify the derivation. As you can see here, express the TPE, that is total potential energy, in terms of the independent variable. Consider all spring and energy due to loading. Simplify the expression. Make sure that no algebraic mistake, otherwise you will get wrong answers. So you make sure you have no algebraic mistake and follow this formula. Expand and simplify the formula as follows. Observe that these are linear equations with respect to ds. Use the equilibrium condition to write down the two equations and rearrange them in a matrix form as shown in this diagram. Two eigenvalues of the coefficient matrix in terms of P are the two buckling loads, that is the P critical, that is K over L, and P critical 3K over L. Buckling mode of 2 DOF spring bar system, that is defined axial load column model. Calculation of buckling mode shape. For each buckling load, substitute its value into the equilibrium equation, which will lead to two linear equations as given. Note that this is essentially an eigenvalue problem where the critical loads are eigenvalues and the buckling mode shapes are the eigenvectors. Eigenvectors have shapes but not magnitude. Therefore, the equation can only have only one is independent, arbitrarily set a non-zero value to D. So let me repeat. For each buckling load, substitute its value into the equilibrium equation, which will lead to two linear equations. Only one is independent. Arbitrarily set a non-zero value to D1 or D2. Use one equation to find out the values of D, D2 or D1. A buckling mode shows how two displacements will relate to each other. The actual values are not important, but their ratio or relative value. Always sketch diagrams to visualize the modes. In general, the number of buckling or modes equation of the numbers of D or F. Another example of use of direct calculation of elastic critical loads is shown here. So you do the procedure as shown. For equilibrium, derivative of theta over derivative of beta should be 0. And you follow the procedure to get the two buckling loads, that is P critical 1 and P critical 2. Direct calculation of elastic load step by step. Identify the independent displacement or angle. Define the total potential energy equation, that is theta. Linearization of theta, that is small angle approximation. Impose first derivative, that is equals to 0. Identify the non-trivial solution. Calculate the buckling mode. The buckling of struts. There are two approaches that can be used to find out the buckling load of columns subject to an axial compression. That is the classic Euler solution which will give the exact buckling load, but need to solve a second order ordinary differential equation, that is ODE, and thus is hard for complicated cases. The second one is the Rayleigh's method, which is simpler and follows the same TPE approach as the spring bucket, but only one buckling load can be found. It may be an approximation which would always be larger than the true value, unless a true deformation shape is used. So in this example, you start by establishing the equilibrium ODE equation for the beam, use the moment and deflection relationship, specify the correct boundary condition. Find the general solution to the second order ODE. Apply the boundary condition to the general solution. The existence of non-zero or trivial solution lead to an equation that buckling load should satisfy. For each load, the corresponding non-zero solution is the buckling mode. There are infinite number of buckling loads since a column is a continuous solid, but only the lowest one has the practical engineering meaning. So you can see buckling, strut, and Euler load, that is the Rayleigh method. Rayleigh method for buckling of a column. Assume a deflection shape using a function with one unknown parameter. This function only needs to satisfy the boundary condition. Better assumption of the shape will give better approximation to the true buckling load. Evaluate the integral to find out the expression for the shortening of the column at the top. Use small deformation assumption to find the integration. Further evaluate another integral to determine the strain energy of the column under bending, as you can see here. Write down the expression for TPE, that is positive equilibrium. The first derivative equals to 0. The non-trivial solution leads to the buckling load. The assumed deflection function is the buckling mode. The buckling load found will be the upper bound of the true buckling load. The accuracy of the obtained buckling load will be determined solely by the quality of the assumed function. Try more possible deflection shape can improve the accuracy. Choose the smallest value as the final answer. So you can see the reason we obtain the exact load here is because we use the exact buckling mode shape as assumed deflection. When you choose different deflection shape, different and approximate buckling load will be obtained. The exact buckling load will be the one with the smallest value amongst all the possible value deflection shapes. Alternate derivative based on the second derivative of the potential energy, as shown here. pin-ended strut, deflection constraint at the midpoint, as shown in the figure. Real strut have initial imperfect shapes. So the solution will be as shown in the figure. Stress in buckling strut, that is the yield limit. In buckling state, stress are due to compression and bending. The compressed stress across the section is obtained as shown. Thanks for watching. I will see you in another episode. That is, we will now go to part 2. Thanks.